In the annals of human innovation, few advancements have captured the global imagination quite like artificial intelligence. From revolutionary language models to sophisticated autonomous systems, AI is redefining industries and daily life. Yet, this rapid ascent is built upon a foundation often overlooked: the microchip. According to a recent report by Deloitte, the computational power required for leading AI models is doubling every few months, creating an unprecedented demand for specialized semiconductors. This surge has brought us to a critical juncture, a paradox where the very technology driving progress faces a fundamental bottleneck in its physical creation. At the heart of every AI breakthrough lies the silicon wafer, meticulously crafted into microprocessors. These tiny marvels, often no larger than a fingernail, contain billions of transistors, acting as the silent engines of the digital age. But their creation is far from simple. As industry analysts at Gartner point out, the manufacturing of advanced semiconductors represents one of humanity's most complex engineering feats. It requires staggering precision, immense capital investment, and an environment almost entirely free of contaminants. This intricate process is where the true challenge begins, transforming raw materials into glowing digital brains. The microchip paradox, as coined by analysts at Bloomberg Intelligence, describes a critical tension. As artificial intelligence demands increasingly powerful and specialized chips, the ability to produce these chips is reaching its physical and economic limits. This isn't just about more chips, it's about the bleeding-edge components necessary for our specific workload. According to NVIDIA's recent investor calls, the demand for their high-end GPUs, crucial for AI training, has consistently outstripped supply for the past 2 years. This fundamental imbalance is sending ripple effects across the global economy, from startup valuations to national security, driven by a thirst for more advanced server systems. The journey of a microchip begins with sand, specifically, ultra-pure silicon. This raw material is melted and grown into enormous monocrystalline ingots, often several feet long and weighing hundreds of pounds. As documented by Texas Instruments, this crystal growth process occurs at extremely high temperatures, requiring meticulous control to ensure atomic perfection. These ingots are then sliced into thin, circular wafers, the foundation upon which billions of transistors will eventually be built within futuristic silicon wafer manufacturing facilities. It's a foundational step, demanding immense energy and an environment free from imperfections. Once sliced, these silicon wafers enter the domain of the cleanroom, an environment meticulously maintained to be thousands of times cleaner than an operating theater. Here, human interaction is minimized, replaced by an intricate dance of automated robotic systems. According to ASML, a leading supplier of chip-making equipment, even a single speck of dust can render a multi-million-dollar wafer useless. These robotic arms precisely transfer wafers between machines, applying layers of material and etching patterns with unbelievable accuracy, showcasing the peak of industrial automation necessary for nanoscale manufacturing in high-tech robotic cleanrooms. The true magic happens with lithography, where complex circuit patterns are projected onto the wafer using extreme ultraviolet (EUV) light. This process, pioneered by companies like ASML, allows features to be etched at resolutions measured in nanometers. Individual atoms are practically the next frontier. As explained by Intel's chief technology officer, these EUV machines are among the most complex and expensive pieces of machinery ever created, each costing hundreds of millions of dollars and weighing over 180 tons. They are the backbone of modern chip production, pushing the boundaries of what's physically possible for glowing microprocessor circuits. While general-purpose CPUs handle a wide range of tasks, ARM's appetite for parallel processing has elevated the graphics processing unit, or GPU, to critical status. Originally designed for rendering complex video game graphics, GPUs are exceptionally good at performing many calculations simultaneously, making them ideal for training AI models. As NVIDIA CEO Jensen Huang has repeatedly stated, the GPU is no longer just for graphics, it's the engine of modern AI. Their architecture allows for the massive matrix multiplications fundamental to deep learning, driving unprecedented demand and propelling companies like NVIDIA to new market highs for their advanced server systems. The surge in AI demand has dramatically reshaped the corporate landscape. Companies at the forefront, particularly NVIDIA, have seen their market valuation skyrocket. Financial reports indicate NVIDIA's stock price experienced over a 200% increase in 2023 alone, driven by unprecedented orders for their AI accelerators. This isn't an isolated event. Intel and TSMC have also announced multi-billion-dollar investments in new fabrication plants and research, signaling a global race for semiconductor supremacy. As analysts from Goldman Sachs observe, these investments reflect a long-term strategic pivot towards AI infrastructure, fundamentally altering the corporate stock market charts of tech giants. The destination for many of these advanced chips is the hyperscale data center, the very brains of artificial intelligence. These vast complexes, sometimes spanning hundreds of acres, house tens of thousands of advanced server systems, each packed with GPUs and specialized AI accelerators. A recent report by the International Energy Agency highlights the enormous power consumption of these facilities, with some data centers now drawing as much electricity as small cities. The quest for faster, more efficient AI processing fuels an endless cycle of demand for more powerful and compact server architectures, continually pushing design boundaries for glowing microprocessor circuits. The journey from raw silicon to a finished microprocessor is a global ballet of specialized components, materials, and machinery. This intricate supply chain spans continents, with critical steps often concentrated in a handful of regions. As a detailed analysis by McKinsey & Company revealed, disruptions at any single point, from a natural disaster in a specific manufacturing region to geopolitical tensions, can cascade, creating widespread shortages. The sheer volume and complexity of AI chip demand have exposed the fragility of this globally interconnected system, pushing the futuristic silicon wafer manufacturing process to its breaking point. At the apex of this complex supply chain sits Taiwan Semiconductor Manufacturing Company, or TSMC. According to a report by the Rhodium Group, TSMC alone produces over 90% of the world's most advanced chips, including those vital for cutting-edge AI. Their state-of-the-art fabs in Taiwan are technological marvels, operating around the clock with unparalleled precision. This concentration of advanced manufacturing capabilities makes TSMC an undisputed linchpin of the global tech industry, but also a point of considerable geopolitical concern, given Taiwan's unique status. The world's AI future literally runs through their high-tech robotic cleanrooms. The strategic importance of advanced microchips has propelled them to the forefront of international relations. Nations now view semiconductor manufacturing capabilities not just as an economic asset, but as a matter of national security and technological sovereignty. As observed by the Center for Strategic and International Studies, the scramble to secure domestic chip production is intensifying, leading to new alliances and heightened trade tensions. The control of this vital technology grants immense power, making the microchip paradox the central theme in the geopolitical landscape, shaping everything from defense strategies to economic dominance, impacting the corporate stock market charts globally. In response to these vulnerabilities, governments worldwide are enacting ambitious policies. In the United States, the CHIPS and Science Act, signed into law in 2022, allocates over $52 billion to boost domestic semiconductor research, development, and manufacturing. According to the Semiconductor Industry Association, this legislation aims to reduce reliance on foreign supply chains and re-establish American leadership in advanced chip production. While lauded as a crucial step, analysts like those at the Brookings Institution caution that building new fabs takes years and faces significant workforce challenges, highlighting the long road ahead for futuristic silicon wafer manufacturing. Once a dominant force, Intel has faced significant challenges in recent years, losing its lead in advanced manufacturing to rivals like TSMC. However, with the renewed focus on domestic production and substantial government incentives, Intel is investing heavily in a comeback. CEO Pat Gelsinger outlined a strategy to reclaim process leadership by 2025, committing tens of billions to new fabs in the US and Europe. Financial analysts at J.P. Morgan note this aggressive expansion, though costly, is critical for national and corporate strategic interests, potentially altering the landscape of microprocessor circuit manufacturing significantly and impacting corporate stock market charts. Building a state-of-the-art semiconductor fabrication plant, or fab, is an astronomical undertaking. Industry estimates from SEMI, a global electronics manufacturing association, suggest that a single advanced fab can cost upwards of $20 billion and take several years, often 3 to 5, from groundbreaking to operational readiness. This immense capital expenditure, coupled with the need for highly specialized equipment and an expert workforce, creates significant barriers to entry. The cost curve is steep, and every new generation of chips demands even greater investment, illustrating the immense financial burden of keeping pace with ARI's demands for glowing microprocessor circuits. Beyond shrinking transistor sizes, innovation in advanced packaging is becoming crucial for AI performance. This involves integrating multiple chiplets, smaller, specialized functional units, onto a single package, creating a powerful, interconnected system. Companies like AMD and Intel are pioneering techniques such as 3D stacking and chip-on-wafer technologies, as reported by E! Times. This allows for greater functionality and bandwidth within a smaller footprint, crucial for advanced server systems. These innovations are helping overcome some of the physical limitations of traditional monolithic chip designs, squeezing even more power into glowing microprocessor circuits for AI. The computational hunger of AI extends beyond manufacturing into its operational phase. The advanced server systems powering AI models consume vast amounts of electricity, primarily for processing and cooling. A recent study by Nature Communications projected that global AI data centers could consume as much electricity as countries like Sweden or Ireland by 2027. This burgeoning energy footprint presents a significant challenge, driving innovation in energy-efficient chip design and sustainable data center operations. The glowing microprocessor circuits within these centers are efficient, but their sheer number creates an immense draw on global energy resources. The ambition to build more domestic fabs and innovate faster is hampered by a critical shortage of skilled talent. From highly specialized engineers capable of designing next-generation chips to the technicians required to operate and maintain multi-billion-dollar high-tech robotic cleanrooms, the pipeline of talent is insufficient. A report by the U.S. Department of Commerce indicates that the U.S. alone will need hundreds of thousands more skilled workers in the semiconductor industry over the next decade. Universities and vocational programs are struggling to meet this demand, creating another bottleneck in the global effort to overcome the microchip paradox. The microchip paradox is not a temporary anomaly but a defining challenge of our technological era. The future landscape will likely be characterized by continued massive investments, intense geopolitical competition, and relentless innovation in both chip design and manufacturing. As noted by the Semiconductor Research Corporation, breakthroughs in materials science, quantum computing, and neuromorphic chips could offer new pathways, yet scaling these to meet ARI's demands remains monumental. The glowing microprocessor circuits of tomorrow will be the result of today's unprecedented race to build capacity and push the boundaries of physics in futuristic silicon wafer manufacturing. As AI continues its rapid evolution, its demand for computational power will only grow more insatiable. The intricate dance between digital ambition and physical limitations will define the pace of global technological progress. The paradox, where the very engine of innovation struggles with its own material scarcity, forces a fundamental re-evaluation of supply chains, national strategies, and corporate investments. The future of artificial intelligence, and indeed much of our interconnected world, hinges on how effectively humanity can scale the silent engines that power it, from high-tech robotic cleanrooms to the glow of advanced server systems. This story is still unfolding, a testament to ingenuity, resilience, and the relentless pursuit of progress.